Hello guys, here I'm presenting a demo for how to easily create new kernels with DP-HLS. This is a roadmap for today's demo. We'll start with simplest Smith-Waterman kernel with linear gap penalty, and then we will show the changes to make it a Needleman-Wunsch algorithm with linear penalty. And then we'll also show how to extend this linear Smith-Waterman into a Smith-Waterman kernel with a fine gap penalty, and also how to create a kernel for protein sequences. So now let's start with the Smith-Waterman. This is the scoring equation for with a Smith-Waterman algorithm with a linear gap penalty. And each algorithm naturally comes with a set of parameters that define the basic properties of the equation of the algorithm. And we specify those parameters in parameter h. And first of all, the is the number of scoring equations, which usually equals to number of scoring matrices. Here with the linear gap penalty, we have only one scoring matrix, so we can do this by simply define this n layers macro to be one. And also we need to define the sequence alphabet. Since we are currently building a kernel targeting the DNA sequence, so 2 bits is enough to represent each nucleotide, and we can define this character type by AP unsigned int 2, and this AP unsigned int is from the lattice arbitrary position number library. And also, we can specify the scoring position of the scores. In this example, we can define the scores to be 16 bits fixed point number with 10 integer bits. And we define the type T to achieve this. And also, the as function chooses the penalty to apply in those scenarios. The match score, mismatch, and gap penalty if there's a gap. We can do this by simply defining a struct called penalties, and the value of those penalties can be specified by the program host during the runtime, and they're accessible when we are computing the scores in the kernel. Now let's take a look at how its scoring function and traceback is defined in the actual code. This is the DP-HLS repository, and in this kernels folder, we provide a list of examples uh, for the kernels we implemented with DP-HLS. And for each of those kernels, there are 2 files. The first one is a CPP file, including it includes the user-defined functions for the kernel and the params.h, which includes the user-defined parameters, as we just introduced. And this local linear kernel corresponds to the linear Smith-Waterman. So this scoring computation is defined in the P compute function, and it's very intuitive since it matches closely with the algorithms we just presented. And here it's just comparing the insertion and deletion scores, and also the match and mismatch scores. And then those if statements are used to find the overall maximum scores between those 3 scenarios and 0, and set its corresponding traceback pointers. Then for the traceback, we can define a traceback logic in this state mapping function. It maps the current traceback pointer and the current state into a navigation. Navigation is whether we move left, up, or diagonal in the scoring matrix, which equals to the insertion, deletion, or match and mismatch scenario. Here, we have several if statements to map this. So this means if the traceback pointer is diagonal, then we can set the navigation into diagonal. And the rest of the condition is all similar. Now we are ready to move to the Needleman-Wunsch algorithm. The scoring of those 2 algorithms are very similar, and the difference is that in the Needleman-Wunsch algorithm, we don't clip negative scores to 0. And also there are a difference in the scoring initialization. The scoring initialization is defining the initialize score function. And in Smith-Waterman, we simply initialize all the scores to 0. But in Needleman-Wunsch, we need to apply the initial scores with a gap penalty. And this can be simply defined in this initialization loop by applying a gap penalty at each iteration. And also the scoring of those 2 uh, algorithms are basically the same, except in Smith-Waterman, we are clipping the negative value with this condition check. But in Needleman Wunsch, we can simply delete those conditions. And also in Smith-Waterman algorithm, we need to start a traceback from the overall maximum score in the scoring matrix. And this is done by this update PE maximum function, which for each iteration checks if the local maximum of the processing elements is uh, smaller than the current score and update those scores. But in the Needleman-Wunsch algorithm, there's no need to do this runtime check because we always know that the tracebacks are from the bottom right. So we have those logic to pre-compute the coordinate to start a traceback. And those are all in the examples we provided. So people can just copy and paste those code for the global alignment algorithms. And also there's a change in the traceback because in the Smith-Waterman algorithm, we stop the traceback if we hit a zero score or at the boundary. But in the Malmonch, we always trace back to the origin. So we can just simply remove this condition check to early stop the traceback in the traceback function. And now we're ready to see how can we create a smooth movement with a fine gap penalty from the linear version. So with a fine gap penalty, there will be three scoring equations. As a result, we need to change the n layers to three by simply change this macro definition. And also it introduces two new penalty scores, which is the penalty for gap open and gap extend. Those two entries are added to the penalty struct. And also the initialization is very similar. We just need to define this score into a three tuple, and each of them are being zero or negative infinity. So now let me show how the code changes are needed. This is a comparison of the kernel compute function for affine Smith-Waterman and linear Smith-Waterman algorithms. And the affine scenario is a little bit more advanced because it computes the scores for two more matrices, which is the insertion and deletion matrices. This left pref and up pref means the cell score on the left and above the current cell. And this indexing is indexing the which scoring matrix it is currently accessing. And by our definition, score matrix 0 is the insertion matrix, and matrix 2 is the deletion matrix, as represented in the code. But the rest of them are very similar, which is to find the maximum between the insertion, deletion, and match mismatch scores, and also 0, and set its corresponding traceback pointers below it. Next, we need to change the traceback logic in the state mapping function because the affine gap penalty results in a more complicated traceback logics. This time, we actually need to use this state variable, which represents what is the current score matrix we're at, and assign it with the new scoring matrix according to the traceback pointer values. Okay, now we are ready to move to the Smith-Waterman with for protein sequences. The scoring of those two algorithms are very similar, except that the S function in the protein version is a 20 by 20 substitution matrix. And we'll talk about how to implement this change. And also for demonstration purposes, this protein Smith-Waterman kernel has no traceback. And we can turn off the traceback very easily by simply define this no traceback macro. The first thing to do is to change the alphabet. And before for DNA sequences, 2 bits is enough to represent those 4 nucleotides. But in the protein version, there will be 20 amino acid, and 5 bits is required to represent all of them. So we just change this 2 bits unsigned integer into 5 bits uh, and define it to be the character type. Also, to enable enough bandwidth for each PE to access this below-sum matrix, each PE is allocated individual BRAM to store the entire matrices. And during the runtime, each PE access their local uh, access their local substitution matrix. And this feature can be turned on by simply define the local transition matrix macro and also define the uh, transition matrix size. So in this demo, we show how we can easily create new kernels by leveraging an existing kernel in DP-HLS. And you can find more detailed tutorials and examples in our documentations and open source repository in the links below. Thanks for watching.